Hello, everyone. This is a new IITT talk, a new session. It's to me the most important because I'm going to be interacting since I love this subject. It's kind of my specialty, and I'm so excited. I think this is number 27. And today we have with us experts and people from industry and academia. And I'm going to introduce you by sharing my screen. So with us today, we have all the way from Korea, Professor Sangseom Jeong, professor at the University of Yonsei University in South Korea. He is the vice chair of TC212. And guess what? He is also my friend since we were together in grad school at Texas A&M University. And I'm so happy to have you here again and see you kind of live. So welcome, welcome. Also, Mr. Mario Terceros from Bolivia, a TC212 member. Design of Deep Foundation is his expertise. We're going to hear about it. And then we have Mr. Raffaele Cesaro, Dr. Raffaele. He's a postdoc now in Italy at the University of Campania. The title is New Developments in Pile Foundation. It's always good to learn more and something new. And with us also from Singapore, Ms. Rara doing Noviarti. She's going to talk about the challenges in Indonesia from a young engineer's perspective. And I can't wait to hear your presentations. And I'm going to jump directly to give the stage to Professor Sangseom. So I'll stop sharing. And please, if you put on mute so that there are no background noise, unless you have to interact. Remember, this is an interactive talk. So if you think we can interfere at a certain stage to complement the analysis or the presentation, it would be good for all of us and the viewers. The floor is yours, Professor.
Okay, thank you, Mr. Mike. It's okay for you, all of them? Okay, just I'm introducing some TC212, the deep foundations, and based on some
It was showing okay.
a second. Okay, I'm starting the TC212 deep foundations based on some content. First, I'm talking about TC212, and then I'm just briefly summarizing recent activities in TC212, and then I'm talking some foundation design of past, present, and future, and then I'm just talking about deep foundation design concept, and then I'm talking some interactive analysis, and finally, I have some case study to have two case studies we have on bilaft foundations. Okay, first, what is about the TC212 is deep foundations, and this committee is originally hosted by Italian society, and now we have a total 89 members with Dr. Mandolini from Italia as a current chair and 25 corresponding members, including Dr. Kazenbao, and 61 nominated members with Dr. Mario Tercero, who is also presenting today. The main objectives of TC212 are firstly to promote knowledge exchange in the foundation engineering, secondly to develop new guidelines and recommendations for the design and application of pile raft foundations, third to assist the coordination and execution of conference and technical sessions, and finally, to reduce the gap existing between the theory and practice in the field of the foundations. Our committee is organizing some activities worldwide. The most recent event was held in Belgium on May 21st this year as a part of the SAGE SAND project. Later, load blind prediction competition was organized by Dr. Mandolini. The competition focused on the prediction of the lateral load deflections response of two hollow steel monopiles for wind farm foundation. The competition participants were coming from over 10 different countries. And another second, some prediction purpose, ultimate capacity assessment, the pile prediction event organized by Dr. Bent Felenius in regard to the forthcoming static loading test on a driven 18-inch pipe pile in Mobile, Alabama. The survey was conducted among 94 participants from 26 countries to ask for pile head load movement curve and force distributions. And so you hear is another some ISSMGE Sydney conference.
Sangseom,
Yes,
these
sir.
already have results, or
Yes.
we can still compete?
You don't need to just to mention about.
Are the
Okay.
results out already, or we can still compete? Is it still open, the first one?
Yes, it's still open to the public in this year. You mean the first
So,
one? What do you mean?
go ahead, go ahead.
Okay. There are several some activities in 20th ISSMGE, the Sydney, and another one is 27, 17 in Korea, the 19th ISSMGE conference, and the other, some other conference held in 1st and 3rd in Bolivia in the last 2017 and 2019. The foundation design approach has been improving significantly over time. If in the past capacity-based design was prevalent, in the future it will lose its singular importance, and settlement and deformation analysis will be a required feature of design. Also, allowable stress design dominated all the method, and now we use reliability-based design framework such as LRFD and Eurocode here. The relatively recent shift to load and resistance factor design has caused uncertainty about the assurance of a design in some cases. Another techniques has also changed from non-interactive to interactive analysis, leading to more accurate interaction problems of superstructure, foundation, soil interactions. Now you look at the types of piles. The past has widespread use of driven piles and board piles, as well as pre-boring, precast piles, steel piles, and micro piles. Today, the innovation was pushed toward large diameter piles, monopiles for offshore and pile raft foundation. Lastly, due to growing emphasis of sustainability, there is increased attention on energy piles, decarbonization, and reuse of existing piles. Okay, let's go into the deep foundation designing. You can see here, you can shallow and deep foundations here on the left figure. The figure is showing is a shallow foundation, group piles, pile loft foundations. A typical pile group foundations here is not in direct contact with the soil. And however, pile loft, the loft is in direct contact with the soil. In the designing process on the criterion, the load settlement curve is showing of these foundations to satisfy the working load of building. We can control the settlement corresponding to the working load. The pile raft foundation is highly affected by the three-dimensional interaction between the soil, pile, and the raft, has been recognized and proved to be economical alternatives to conventional pile group foundations. You can compare the pile group and pile raft foundation here, a reduction in number of lengths of pile, reduction in the internal stress and bending moments in a raft by optimal arrangement of piles beneath the raft. Let's say I'm just introducing the interactive analysis. You can see in the left just figure, there is a superstructures and some substructures. We can go into all together to analyzing some of the analysis by just interactions called is interactive analysis. To have this kind of interactive analysis, we can see some kind of raft flexibility. It's very important to consider the raft flexibility. By considering the flexibility and the deflection of the raft, we can overcome some limitations of existing method. The primary limitation of this method is that the membrane effect of the flexible raft. In the present method, a numerical technique is developed to combine the soil and the pile head stiffness with the stiffness of the raft. Here is I'm considering the raft is a flexible behavior, like this kind of some the behavior of the flexibility of the raft into the consideration, and then also we can finally some kind of raft. It's a flexibility, and then including some of the soil support systems over here, and to consider to soil structure intentions. Here, to involve some soil spring coupling effect, also the present method is proposed to improve the interactions of raft soils pile systems. And then finally, we can propose some analytical method, like some kind of some raft flexibility. Also, we can include some kind of some beam elements to consider some kind of piling systems with a linear soil spring system or nonlinear systems. Also, this is proposed to the model to analyze both flexible pile raft and raft foundations. Also, this method was used to examine the design of the high-rise building for estimating the overall settlement behavior of the foundation. Let's go into the case study of pile raft foundation, especially in weathered soil rock cases here. I call this a Yonsei case. I can just briefly summarizing. Here you can see here some kind of load distribution ratio of the pile raft foundation of the first engineering hall at Yonsei University was measuring during the construction. In this case, the load distribution ratio of the raft portion was quantified. Is this figure showing the schematic of the objective structure and the portion of the foundation? The overall foundation of the structure consists of several independent pile loft, and each pile has a loft 5 piles, test piles over here. And the geometry of the loft looks like 3.1 meter and 3.1 meter, and thickness about 1.1 meter. And then the field measurement was performed for about 300 days from the start of construction. And then this figure is showing schematic representation of instrumented pile is shown in this figure. About the total 70 electrical resistance strain gauges just were attached to the test pile, and 3 pressure cells were placed in between the loft and the resting soil. And the measured and the calculated result is shown in this figure as a relation between the settlement here with the total load applied acting on the pile. And then based on the measurement and the numerical result, this is the right figure is showing the load settlement behavior of the real, just measured some kind of this measured one for the total pile, just total applied loading. And this is the load just resisted by the pile itself. And then based on some kind of numerical approaches, we can predict some of the some prediction results compared to the observed ones. And another one case is of the pile loft foundation with weak mudstone rocks. You can see here is the cases is based on the loft settlement of the Pohang Tower in Korea. The tower was height of the 176 meter and consists of 45-story superstructures and 4-story just the substructures. And then here you can just the construction stages. The ground surface is excavated up to the 20 meter over here, and then the piles are installed bearing to mudstone rocks. As shown in this figure, the cases of the original pile loft, the designing purpose and geometry, and the subsequent the response of optimal group geometries analysis. Based on some kind of analysis using some kind of pile loft designing purpose, and then we can reduce some of the pile lengths into some kind of optimal length from 45 to 30 meters using pile loft analysis to satisfy some of the settlement calculations in terms of the comparison between pile loft and the group piling. The settlement is all satisfied. Also, we can check some kind of some member forces, especially in axial forces and load sharing ratios, and then the pile loft can satisfy all of the some kind of the member forces compared to some of the some group pile analysis is not satisfied the result over here. So by satisfying this kind of all settlement criteria and the member forces,
yeah,
yes, sir.
Sorry to interrupt.
Okay.
The piles. Oh, you're finishing. Can you go back 2 slides?
Sure. That's fine. So the case is showing.
Yeah, they're going from original to optimized. You also said smaller pile diameter. How much was the first pile? How big was the diameter? And then how much smaller it was for the optimized design? Do you
Just
know?
the pile diameter is about one is a ballet pile, so it's a square pile. So this is I don't reduce the pile diameter, only we can
Only
control
the length.
the length of the piling to satisfy all of the design criteria. And then we can finally find out the optimal design, the geometry of the group pile systems by using some kind of pile loft foundations. That's the concept you are using, designing, or some of the pile loft foundations in the real field. In this case, the construction of the buildings already constructed and is operating now. This is the end of my presentation. Thank you for your kind attention.
Thank you so much. Thank you so much. I think we're ready for more excitement with Mario. If you
Thank
stop sharing your screen, Professor, so Mario can share his.
Okay.
Floor is
Okay.
yours.
Okay, thank you. Now it's I will speak more from the practical point of view, the industry. So I will try to show quite simple concepts in order to be more practical for all the users of the industry. The name of the presentation is Knowledge Instead of Faith. And I will present three types of concepts that can help us going from the knowledge. Oh, what's happening here? I don't know why it's not passing the next one.
It's not
Oh.
shifting slides.
Yeah, it's not. I don't know why. It was working well. Wait a second. I will. What's happening here? Sorry, I will stop sharing and excuse me. I don't know what's happening here.
Yeah. Check it outside and then restart.
Yeah.
No problem.
Okay. It works. It works here. I hope it works now. Sharing. Share. Okay, now I will put the full because here is working.
Yeah,
Yeah, it should.
it's
Okay.
working.
What are the tools we use for the designs in general? First of all, soil investigation, which are never enough because we just take some samples or some tests in a very little amount of the whole body of soils. It works where we have quite homogeneous soils, but in case like my case where we have sedimentary hydraulic soils, we can have very big variations in very short distance. So that's one of the points we use to design. Then with the soil investigation, we go to the soil model. And all what the professor presented can be derived from that. So what is the soil model we are using? The old-fashioned is, of course, to use the just simple formulas, some experience. Now they are much more sophisticated mathematical models, but always we are depending on the soil investigation and the soil parameters, basically. The other point to design that is a big problem in several places is that the designer decide what is the construction method, but is not always respected in the field, mainly in the cast in situ piles. It's not the same to drill with casing than without casing, with mud, with bentonite, or with CFA, the normal one or the partial displacement CFA, and so on. So it's very important to respect what is included in the construction method.
I want to, Mario, I want to mention when I was doing research, we compared different construction technique in the field by just by forgetting the mud or the bentonite slurry over the weekend, simulating that the pump is damaged, and we came back Monday and poured concrete and did the same pile with good cleaning. The difference in capacity and even the curve was 4 times.
I believe it. Totally.
Unbelievable. Four
Yeah.
times. So
Yeah.
just to complement what you were saying.
Yeah. For example, we have measured and
High
with
quality is
instrumentation.
very, very important. Yeah.
Yeah, and that's because now we are using in the 100% of our project the full displacement pile, which provide 4.5 times more than the drill with bentonite. So the technology is very important, and of course, the loading test. If every single project would be designed with the help of a loading test, everything will be different. We are trying to do that in almost all our projects. But it's not always easy to convince the clients. No? So what is the main concern? It is possible to predict the response of a pile. Okay, that's one of the in our experimental site we had here that professor mentioned. It was in 2017. That is for one type of pile. This for another. This one, the left one is a CFA, and the second one is a drill under bentonite. The red is the actual test. So if we compare the highest value and the lowest value, the difference is roughly 600%. So who is wrong? Because here we provide a huge amount of soil investigation, but that's the true in the prediction. Then with the real curve, we ask to the predictors to define what is capacity. Here you have. It's not a single concept of capacity, which I am totally convinced we have to start forgetting this concept of design with capacity plus the safety factor. The design with settlements should be the base of the modern way of designing. Some comments. These are the very old curves for the tip resistance of driven piles for different authors. Depending on the author, you can have the NQ 30 or 220. Okay. Nobody is yeah. Yeah, nobody's wrong, but the problem is what's happening here. First of all, we have to know what is behind the model that gave the curve. If we don't know that, we will use it in the wrong way. Okay, so what we need for a good design and a good foundation is to get reliable data. First of all, now the modern equipments, they give you a lot of information. This is just for one CFA where we use the machine with a pipe as a penetrometer because it was in very soft clays, and we use those parameters to adjust the design. And then we tested, and the results were with variation of plus minus 10%, according just using the machine data we got. In the other case, the full displacement piles, it allows us to see if the analytical pile length is right or not, because the truth is in the soil, it's not in the paper. So with a good support, we can do that. So we get for the 100% working as a penetrometer, the tool of drilling, we get a lot of information like torque, force, etc., which is very helpful once you know how to correlate with the values. So another question is, why don't we install systems that can give us information also in the 100% of the piles? This technology, the expanded body, is basically a larger, is a steel pipe that is folded, installed on the tip of the pipe of the pile or of the anchor, and then injected. So you pass from 12 centimeters to 880 centimeters. So you imagine the forces involved in such expansion. So it's not only because the enlargement of the base, but also because the compaction and the shear strength improvement, the stiffness improvement of the soil. So, okay, this is a very basic way of showing how it expands. What we do is we measure in every single element the horizontal stresses. So, and the curve I will show you, that's in the case of the anchor, the curve is a very large displacement pressure meter, and okay, that's are the standards where it is, and the shape of the curve is exactly the shape of a pressure meter in case the pressure meter would have been able to get at the limit pressure as we go. So we have the initial phase, we have the elastic phase, and we have the yielding phase. So we can get not only the limited pressure, but also we can know with the curve the type of soils, the type of installation we had, and we can derive from the pressurometric theory several other parameters. This is just one calibration curve for the inflation versus the real volume and the real diameter. So here you see a very sandy soil. And in that case, we compare always which is the lowest value of resistance. If it is in this peak or at the end of the injection, and we use this for the quality control. Look here, a very, very loose sand. Just using the expanded body, we got an increase of, okay, let's say 0.2 to 1.6 megapascal. We could increase the behavior in 8 times. Without expanded body, it would have been just a pile in this sense would have been much less resistant. This is a case where we have a leakage, so we can control that. This is a
So
case
it's
in a, yeah.
So you're saying it's a mega pressure meter test and a pile
Yes.
strengthening method.
Yes, and increasing the size of
I like
the
it.
base. Yeah. Okay, this is
And
another.
manufacturers, there are manufacturers you mentioned from I barely saw that Switzerland, or who's
No, it
manufacturing
was
those tubes?
invented in Sweden, and then we made an
Sweden,
agreement with
Sweden.
them because it's not anymore producing in Sweden. Now we produce in Bolivia and Brazil, and we have installed, I will show
Nice.
you more than 40,000 of these elements. Here's a very interesting case where we have a bentonite pile and a full displacement pile. This one is much shorter, and the results were also very, very impressive. In this case, we measured the friction to be 4.5 less in the drill piles than in the other one. Those are the models
Nice.
that we just, it's not important.
How much in US dollars for each, let's say
Okay,
1.2 meter?
you know, it depends on, okay, on the quantity and things, but our commercial species, it costs the double and it resists more than the triple, because that's a point that for the clients to understand more clearly. And in case of micropiles, the increase is about 6 times. So there is important to design which size of expanded body we want, because we have from 300 millimeters in case of very stiff soils or very soft rocks, up to 800 millimeters. And now we are developing the one with 1.2 meters in diameter. But the price
Very
will be,
exciting.
yeah, the
I
price
have
will be,
one more question. Sorry, I'm
yeah,
so excited.
sure.
I can see the benefit for uplift, does it take uplift? Is there a connection in terms of tensile steel or just vertical compression?
No. It uses anchor too. In anchors, I think I have an image here. It's a okay. First of all, you can install with whatever you want because it's a simple thing. This one, the case of the right was in Stockholm in very soft clays where they push with a jack down to the granite. So it's very easy to work in very small places or in big ones. But
So the tube can take tensile forces?
yeah. I want to show you
Okay,
that. It was originally designed for anchors. In tensile forces, we can increase 4 times against a typical
yeah,
anchor. And in compression, of course, it's also that. This is a typical report we get with the
yeah.
expanded bodies and with,
Uplift,
yeah,
uplift design, it's so good for warehouses or
no,
wind
uplift,
turbines or
uplift, and also for anchoring, retaining walls
lateral.
and this type of things.
Yeah,
We
wow.
also have developed a post-grouting in very loose sands. It helps very much with the settlements. This is one exhumed with post-grouting that was performed for a doctoral thesis, and we make a field test. So you can see several things that now I have no time to explain, but the post-grouting really helps. And here's some loading test. Look this. This is a micropile, the typical one, and this is with an expanded body. You see the difference, in soils, in quite bad soils, because the problem with the micropiles that is mostly used where you have strong soils and rocks and so on. But in places where we have sedimentary soils and we don't have really a good resistant layer, the micropiles is also a good solution. And with expanded body, the benefits are immense. This is a case with an expanded body in this experimental site that Professor mentioned. And you can see if we get, let's say, 25 millimeters, the one with expanded body is around 1600 kilonewtons, and the other is around here, 800. So it doubles the resistance even in a quite big shaft. In anchors, here it is. It was a test in Boston. We have performed 2 projects in Boston, one for underpinning and another for a new project. And this was a test for anchoring. The blue one is the typical one. The other was with a small expanded body, and the other with a 600 millimeter expanded body. See the differences. So it's really very
Wow.
important because you can
So
get,
Mario,
yeah.
sorry, I'm talking too much, but what
No,
can
it's
I
okay.
say? It's very. How
I
thick is the skin of this metal that expands? It's metallic, right?
It's
It's
a, a- it's
folded
a, it's a, it's a special steel of 1 millimeter thick.
one
So
millimeter.
yeah, it is a really interesting, and I will send you later more information because I think
I
you
will
will.
Google it. You don't have to.
Yeah.
I
No, but
want to
anyway,
buy it.
I have
So
several
good.
papers, and there are several investigation papers performed by other people. So it's a very interesting thing. So advantages. It performs a soil investigation at the tip because it is a pressure meter. It gets immense economies in general, and as the capacity or the service load is larger, you use less elements, so the time is also good. Construction time, the high productivity we have here with one of our power machines is always over 20 piles per day, typically 30. And the carbon footprint is important. Here is, I say, over 50%, but the truth is that we have measured in one case that reduction was 80% of carbon footprint because the increasing of the capacity of the piles. So what are the data we obtain for the 100% of the elements? Horizontal stress, injection volume, and pressuremetric curve, where we can get a lot of information. And the last one is this we call a smart cell. It's basically a Osterberg cell, let's say, but we use only at the tip of the pile, because in that case, what we do is we compact the debris, then we compact the soil, and at this level, we have already pre-mobilized and preloaded the soil. So when you load the pile, you will have a totally okay, you will have the same deformation for the shaft and for the tip, and it will start to move really after the force we already put into the soil. So it's a quite simple concept, and the trick here is that we instrument every single cell with a telltale. So we perform a loading test for the 100% of the tip of the piles. And in some cases, when we can mobilize the shaft, we also measure at the top, and we get the behavior, the low movement curve also for the shaft. Okay, those are just pictures. Here is a case where you see it start with 11 of stiffness, and at the end is 115. So it is 10 times more. And in some cases, we have measured an improvement of 30 times more of the stiffness, comparing with the pile in the original conditions. So, okay, here we have more details, but the question is that we really can get major improvements. Here in Bolivia, we have used in several bridges with very good results. And in Paraguay, we have designed a small cell where the typical drill piles, they have a very good cemented sand. The typical capacity or resistance, the load service was around 40 to 50 tons. And with the cell, they are always over 140 tons. So it means that just using an element that provide this improvement of what we have messed during the construction, we can increase the resistance and lower the quantity and so on. And of course, from the carbon footprint point of view, it's really impressive, the results. Here's a case where, just to explain, this original part is because we used to have some welding points in order to know when it starts to open the cell. Then you see the debris compaction was with almost no increase in force, and then the stiffness increasing. In one case, we performing for one bridge dynamic test in one pile with and the other without cell. The results were like it shows here. The tip was 800 tons for 870 tons for the one with cells, and it was 300 tons for the one without cell. So it means that just putting the cell, the resistance of the tip increased 500 tons. And those curves I show because here we have 6 curves, one very stiff, another very soft. Those are the curves for just one foundation block in a bridge. So you can see the difference of the soils because in those rivers that are quaternary rivers, the variation of soil conditions are immense. So here you can see that in case the solution would have been without these systems, it could have had some problems in settlement. So thanks of that, one more pile was included in this block in order to get basically not differential settlement in the block. So again, it's an investigation device. Benefits, okay, cost, time, quality control, and flexibility, because we have used in very small shaft up to 1.5 meters. And with that, you can reduce the length, the diameters, and so on. One of the points I'm always focused in is trying to use the slender piles as possible and with the highest quality, concrete quality as possible. There, the benefits are immense, and from the carbon footprint is also very impressive what happens with that. So the idea was here what we obtain, again, in the 100% of the elements, we know the vertical movement in the toe and the head, the vertical force, force at the toe, friction force, and we can get the low movement curve for the 100% of the pile toes. So I have asked to several friends that are designing what is the real resistance of the piles, and the answer is always, okay, in the one we perform a load test is that. And I say, and in the others, I don't know is the answer. Here we know. So that's why I say we can pass from faith, we believe that the answer will behave like that, to knowledge. Now I know how they will behave. So the idea is to show something more practical from the industry point of view. So what is the idea? To get all these benefits. Less time, economy, highest quality control, and so on. So I spoke fast because the time was not long enough, but thank you very much.
You did well. Great. Very exciting information. Thank you, Mario.
Thank you.
Floor is yours, Raffaele.
Thank you. Thank you. Can you see my screen?
Yes.
Okay, so I'm going to present some recent developments in pile foundation design with a particular focus on the behavior of pile groups under generalized loading condition. That is a topic of particular relevance nowadays, since as a civil engineers, we need to design structures and infrastructures that are increasingly demanding due to the environmental loads, the impacts of climate change, the great urbanization, and so on. So for a pile group subjected to a vertical eccentric load, according to the classic approach, the external load that produces the axial resistance achieving in the most loaded pile is considered the failure load of the group. But we know that this is a very conservative approach, since the ductility of the system is neglected. Indeed, the axial resistance is not achieved in the other piles of the group. So to address this issue, 6 years ago, in 2019, Professor Raffaele Di Laura and co-authors, Professor Luca De Santis and Professor Stefano Aversa, published this seminal work proposing an analytical solution based on the theorems of limit analysis for the construction of the interaction domains of a pile group subjected to a vertical eccentric load. This is based on simplified hypothesis. Indeed, the piles are modeled as rigid plastic independent uniaxial elements, and the contribution of the raft is neglected. I have to say that the interaction diagrams are commonly employed in the design process of shallow foundations, massive embedded foundations, skirted foundations for offshore applications, and so on. But in piling engineering, the routine design is slowly adapting to this new philosophy. So let's look at the practical impact of this design tool. This is an application to a real case history. This is a onshore wind farm in southern Italy. And in this slide, we can see the interaction domain deriving from the conventional design approach, along with the design loads point. So according to the design, the classic design approach, for a fixed pile diameter equal to 80 centimeters, piles need to be 22 meters long. But applying this solution, we know that the real the actual interaction domain is the domain depicted in this slide. So the margin of safety is bigger than expected. So adopting this solution, we can optimize the design, and for this pile diameter, we can adopt a length of pile of 14 meters. So we obtain an overall reduction of 3 kilometers in pile length for the whole wind farm. So this is a great economic gain. But of course, here we are not only saving money, since we are also reduction the carbon footprint, and we know well that nowadays this is not secondary in the design process. So started from this first publication, given the great practical impact, the interest started to grow rapidly from the academia and from companies. So now we have a lot of researchers working on this. So it's, let's say, a hot topic. We also tried to take a step forward, adopting this approach not only for a capacity-based design, but also for a settlement-based design. Indeed, we proposed a solution to obtain interaction domains for a fixed maximum value of vertical settlement of the foundation, or of a maximum value of the cap rotation, that is the parameter that usually rules the design of wind turbines, for instance. Or it's possible to obtain interaction domains for both fixed parameters. So if a maximum vertical settlement and a maximum cap rotation. However, we have to keep in mind that any evaluation about the pile group behavior requires the knowledge of the single pile behavior. But unfortunately, from the results of the international prediction events that have taken place over the last decades, the results are not encouraging about our predictive capabilities. Indeed, looking at one of the last that Mario mentioned, organized within the activities of this technical committee in Santa Cruz de la Sierra in Bolivia in 2017, and I have to say thanks to the willingness of Mario, who spoke before me, looking at the results, some of them Mario already shown, we can see the red curves that are the results of the pile load tests, and the blue lines are the predictions from professionals from all over the world. The results are self-evident, and they don't need other comments, but however, this level of uncertainty is a paradox for me from as a geotechnical engineer, since the evaluation of the single pile behavior and the axial load is the first step in the design process of any deep foundation system. So for this reason, I agree with Mario about the fact that trial pile load tests are always the most effective design tool. But, and this is for, let's say, a practical point of view, but from a theoretical point of view, we have a lot of work to do. And about that, we are working a lot on also on the single pile behavior for the moment, focusing on the behavior of cast in situ piles in sandy soils. And furthermore, with regards to the behavior of pilot rafts, we have to understand and to quantify the contribution under generalized loading condition of the raft that nowadays is still a big issue. Thank you. Thank you for your attention.
Very well done. The latest.
Thank you.
Thank you, Raffaele. Rara,
Thank you.
the floor is yours.
Thank you. Okay. Okay, is it good? Okay. So for today's discussion, I want to talk about the challenge as a young engineer. But firstly, let me brief myself. I mean, like it's a bit confusing. So now I'm a geotechnical engineer based in Singapore since last year. But before that, I spent around like 7 years working on various building and infrastructure projects across Indonesia. So that's why today I will talk about the practice in Indonesia. To start, I think it's a good to have some understanding what the practice that usually I consider when design a foundation. So I try to create a mind map of foundation design you can see here. So actually there is a 6 point that really main point when it comes to design the file.
Sorry, Rara, are you playing the slides? Because we see it small.
Yes, I'm playing the slide. You can't see it.
We only see the first slide in small. I'm seeing this. I don't know if
Oh, wait, let me try again.
even though we tested it.
Yeah, that's why. Oh, how about now?
So we are still seeing the first slide. If you may want to turn off
Sure.
the PowerPoint and then restart it.
Share. Okay,
Or
how
stop
about
sharing and reshare. Yeah,
Sure.
try to play the slides. Let's see.
Okay. How about now? Is it good?
Not yet.
Okay. Sorry.
No panic. Don't worry.
Okay. Is it good now?
Yes.
Okay, that's good. So we are in second slide. You can see my photo here. Okay, sure. So let me, so to start, I think to have some understanding about what the practice I usually use is I try to create this mind map of foundation design that we already talked about this before. We have 6 main points when it comes to design the file. The first one is soil investigation, like Mario mentioned before. Then after that, we have the soil parameter. This involves analyzing the soil properties obtained from the investigation to determine the soil parameter. The next one is, of course, the pile capacity. It comes with the end bearing capacity and skin friction. And we also consider the negative skin friction when we find the soft clay. And the capacity also need to calculate the long-term and short-term settlement, as well as like check the stability and also the group effect. The next one is we calculate the structural load, vertical and horizontal load. And the next one is pile detail. And the last one is quality control to ensure our pile is okay with the pile integrity test and conduct load test. So with that understanding, I will now begin by listing a few challenges I have encountered so far. I'll be sharing by my own perspective, and I will be very happy if we could discuss this point together. So one of the major significant challenge in Indonesia is dealing with thick subsoil. So especially in the coastal and delta region like Surabaya that you can see here. So that this geotomography map showing the 3D visualization that highlight of the presence of clayed silt that you can see in green color. And also here there is a remark that actually the soil have the SPT less than 15. In such environment, one of the main design difficulty is achieving adequate lateral capacity, especially under seismic loading. During an earthquake, lateral forces can cause excessive displacement of pile, which must be controlled to meet the requirement of Indonesian national standard. As a result, in many cases, the number of piles is not governed by vertical load capacity, but rather by the need to satisfy the lateral performance criteria. Another project I encountered involved a thick subsoil layer with SPT less than 2 that you can see here. There is extend up to 35 meters. This highlight in the blue color. This extremely low strength soil that have multiple design and construction challenge absolutely. First one is from the geotechnical perspective. The negative skin friction become a major concern because the upper soil are so weak, they tend to settle more than the pile, dragging the pile downward and reducing the positive capacity. So to address this, we have to extend the pile length up to a more competent bearing layer like this soil layer 4 to ensure our capacity is enough. Second, we have to consider the settlement. The pile cap or wrap must be designed to accommodate differential settlement because of this thick sublayer, and which can lead to the need for larger reinforcement or thicker wrap. And from construction standpoint, there is a risk of pile interaction where driving one pile can cause movement in adjacent pile, especially in this soft ground. So this requires careful planning of the pile driving sequence to minimize the displacement. Then another challenge for me, for a young engineer, is designing deep foundation in this high seismicity area. So because of this earthquake, right, we have the additional load that must consider, such as base shear from the upper structure and also dynamic soil and water pressure acting on the basement wall. So Indonesia's national standard provide detailed guideline for seismic design. It requires that pile design need to design for both minimum and maximum earthquake scenario. As a result, we often need use spiral reinforcement along at least half the pile length, or we adopt larger diameter reinforcement bar to satisfy the limit. Another critical issue is the potential for the liquefaction, especially in area with very loose and saturated groundwater. So my understanding, liquefaction must be carefully evaluated once a site is identified as liquefied. So it triggers the need for additional testing and analysis. This includes advanced procedures such as site-specific seismic response analysis to accurately assess the risk. And another challenge that still ongoing in Indonesia is inconsistency in laboratory testing capability, especially outside the major urban center like Jakarta, Bandung, or Surabaya. In many regions, particularly for small-scale projects such as shop houses, field tests like SPT or CPT are often only geotechnical investigation that conduct. So this one is actually useful, but they provide limited data. Without the proper lab testing, it becomes difficult to fully characterize the soil behavior. So to help bridge this gap, the government issued this guideline. We call it collection of correlation of geotechnical parameter and foundation. So inside this guideline, they put some correlation that we can use that you can see here. The correlation used from the code that usually we use for shallow and deep foundation. And however, it's important to note that this correlation are only a temporary solution. They are not substitute comprehensive testing. Therefore, load testing remains essential to verify the actual pile capacity and ensure the safety and reliability of the foundation system. And yeah, the last challenge that I want to share today is the one that we often face in deep foundation project is related to pile loading test. So according to ISSM, axial compression load tests are a standard method for evaluating pile performance. However, in practice, conducting this test become more complex when cut-off level is much deeper. That you can see here is like 30 meters below ground level. So in one of our projects, we perform a preliminary test pile with the instrumentation. We use VWSG here, like every 3 until 5 meters. Interestingly, we found that even with the double layer geogandel, some lot still can read in this PWSG that above the cutoff level. So the highlight key issue actually current construction method have not yet fully eliminated the influence of friction above the cutoff level. So if loading test conduct without this instrumentation, the measure capacity might not accurately reflect the true in situ condition. So I have a question like, with this condition, is it still valid to conduct pile test at the existing ground surface when the actual cutoff level is significant? Level is much deeper. Yeah, and that concludes my presentation. I truly appreciate the opportunity. I look forward to any feedback or discussion, especially we have many experts here. Thank you.
Rara, beautiful. I like the way you clarified and put together and organized those slides, really. Very nice.
Thank you.
They're challenges and real guidance for all of us and young engineers especially. So we are closing this with your remarks. Thank you all. I don't know if you want to add anything before we close this session. I can't thank you enough. You really are contributing to the international society and the entire community of geotechnical engineers around the world. Thank you very much.
Thank you for
Thank
inviting
you.
us.
Anything you want to add?
Thank you.
Thank you.
It was a pleasure to see you. Bye-bye.
My pleasure.